recording button. Okay. Hello, everyone. Welcome to this week's Scrum seminar. Our first speaker is Shunyuan Mao, who is a grad student from the University of Victoria. Shunyuan is specializing in astronomy and is deeply committed to the application of machine learning techniques in astronomical studies. Shunyuan, welcome. You may want to start the presentation.
Thank you, Zhongri. So, hello everyone. I'm Shunyuan Mao. I'm a PhD student studying astronomy in University of Victoria, and today my talk is about applying machine learning in astrophysical fluid dynamics problems. And specifically, I will give you the applications of deep nets and pins to a specific astronomy problem called planet formation problem. And my advisor is Robin Dong, also from the University of Victoria, and our collaborators include Lulu, Kwame Yi, Sifan Wang, and Paris Multicarrier. So, the broad topic is that we want to solve Navier-Stokes equations in astrophysics. And because using traditional methods such as the hydrodynamic simulation, numerical solver, to solve the Navier-Stokes equation are computationally expensive, we want to find another way. So we use machine learning to solve these equations instead. And in this broad topic, we focus on two kind of problems. The first is a forward problem, and the second is the inverse problem. So for the forward problem is that we want given a group of PD parameters and describe the PD, and we want to get the solution to these PDs. For the inverse problem is that given the solution, the measurement of the solution, we want to infer the PD parameters. And today's talk, I will introduce the three projects we conducted or we're still working on to solve the forward problem and inverse problem. Is that for forward problem, we have two methods. First is the data-driven deep nets to map PD parameters to solutions, and second is the pin. And for the inverse problem, we want to today I want to discuss an iterative forward inverse approach, combining deep nets and the optimization algorithm. And the outline is first I'm going to introduce the Navier-Stokes equations in our problem, why we want to solve these equations in planet formation, and how is this related to astronomy. And then I will introduce the three projects we have conducted. And in the last day, I want to discuss a bit about the future plan. So in astronomy, we focus on a specific stage of the planet formation that is called planet disk interaction. So here is an animation to show you a typical example of the fluid dynamic in this kind of system. So here at the center of this, you can see a red disk. So in the center of this red disk is a star, and there is plenty of gas rotating around the star under the star's gravity. And this kind of system, the star and the gas around it, this kind of system we call the protoplanet disk. You can imagine that the steady state of this disk would be a smooth, atmospheric symmetric system if there is no other object. And at t equal to 0, if we put a planet into this system, you can see a planet at my cursor, the planet is rotating around the star. If we put a planet into this system, the planet's gravity will perturb the gas and influence this structure, just like what I'm showing here. And you can see as the time moves on, even though the planet is small, the planet's gravity can influence the gas distribution in the whole system. And it can even clean the gas in its orbit and create a ring-like cavity in this system. So this is so our main focus is when there are planets in this kind of system, how the planet's gravity can influence the fluid in this system. So this whole system is called protoplanet disk, and there are several properties of this gaseous disk. So this disk, although it's a 3D system in space, because the vertical direction is very thin, we think of sometimes we think of as a 2D system so that we can simplify the equations. And the gas is also hypersonic and it's compressible. So the movement of the gas is things that we are focused on. And first, it is rotating around the star. And secondly, because of planet gravity, the gas is perturbed and the gas is not smooth and not axisymmetric structure. Move on. So to study the gas movement in this kind of system, the physical process of this system is described by the Navier-Stokes equation. And the Navier-Stokes equation composed of two parts. The first is the mass conservation equation, so shown in the first equation. So here the sigma is the surface density in 2D, and the v is the velocity field, also in 2D. And the second part is simply the Newton's second law. So F equal to ma. So A is the acceleration, and we have three force terms. The first is the pressure, and the second is the viscous force, and the third is the gravity. And if we write down the equation in the simplest form, it's just like this. It's very simple. So on the left part is the acceleration times the mass, and on the right part is the three force term. But usually, when we want to solve this equation for them in a numerical solver or using pin, we need to write down all the force terms in detail. So here is a full format of these equations. So we are discussing the equations in a 2D polar coordinate. So r is the radius and phi is the azimuth directions. And still, this is the mass conservation equation, and the second is the Newton's second law. And you can see in the green boxes are the pressure, and in the red boxes are the viscous force. Although it is very complex, but these are just the viscous force. And in the blue box are the gravity. And phi is the gravity potential, and it is composed of two parts. The first is the star, the gravity provided by the star, and the second is the planet's gravity. So these are three equations we want to solve in the simplest situation. And we have three unknown variables. It is sigma, surface density, and VR, radial velocity, and azimuth velocity. And we also need to pair these equations with boundary condition and initial condition, and then we have a well-defined closed PDE, so we can solve it using either numerical solver or using machine learning method. And also, because in astronomy, we do not have a clear understanding or measurement of some conditions, so we have some free parameters in these PDEs. So we have nu is the viscosity coefficients, and the planet mass, the MP here. So these variables are PD parameters, and we usually want to solve the equations under different values of these PD parameters. So we are solving parametric PDs. So how do we do this before we have machine learning? So in the traditional method, we need to solve these equations.
Can I ask you a question? Can I ask you about the how do you know the boundary conditions at the inner and the outer volume?
We do not have a very clear understanding of the boundary conditions. For the inner, so basically when we run hydrodynamic simulation, we usually need to so it's not a hard boundary condition. We need to cut the spatial domain. So basically there isn't a wall, but we need to set up a boundary condition and say, okay, in the boundary condition is the region that we care about, and we do not care about the outside.
So what will you impose here for the pins? Nothing, or will you impose those boundary conditions for the depot net?
So you mean what kind of boundary condition we use?
Yes, yes. Even in the physics informed, for example, the physics informed deponent. What boundary condition would you use?
For example, because there isn't a wall on the boundary, so for example, we set up the boundary condition as there is a constant inflow of gas.
Which one is the final folder for the code? The same.
Kamal, please turn off. Yeah. Okay. Yeah. Go ahead.
For example, the boundary condition we set out that we think there is constant inflow of the gas into the system, and for the inner boundary, we think there is constant outflow of the gas.
I see. Okay.
So we do not have a wall in the boundary, so we just cross the domain of the system.
Okay.
So the traditional method, we solve these equations using hydrodynamic simulations. And we set out the parameters and we solve this equation, and we can get the evolution like what I showed you in the previous movie. And the problem is that a typical simulation is very computational expensive. It can cost 10,000 CPU hours. And if we want to explore the PD parameters space, we want to pardon me. So we want to get the solution for different value of PD parameters. It can be cost 100,000 CPU hours or 1 million CPU hours. It's too computational expensive. We cannot do that. And that's why we want to use machine learning to solve this kind of problem. And today I will discuss 3 projects. The first is the deep net for forward problem, and the second we apply the deep net for forward problem to accelerate the solving of inverse problem. And the last one is using PIN to solve equations directly. So here is the first project. So in this first project, our goal is that we want to build a machine learning tool. This tool can map the PD parameters to the solution of the corresponding PDEs. And once we build this tool, we can apply it to solve the evolution of this disk and apply it to apply it to astronomy. So how we do that is that we build a deep operator network, and this Go machine learning tool we call proto-planet disk operator network, DPD-ONET. And for this DPD-ONET, it's very similar to the version that Lulu in the Lulu's paper, but for our application, the inputs are scalar PD parameters to the branch net, and the trunk net is the coordinates r and theta, the polar coordinates, and the outputs are either surface density or radial velocity or azimuthal velocity. So for one DPD-ONET, the output is one of these 3. We have 3 independent DPD-ONET to predict these 3 unknown physical variables. And this is this architecture. We modify this DPD-ONET architecture, and I will explain it in the next slides. But basically, we build this network and we train it with 450 simulations, and we get a satisfactory fit to all the PD solutions. So we did some minor modification to the original DPD-ONET architecture. And that's the difference is mainly on this part. In the vanilla DPD-ONET, for the output from the branch net and the output from the trunk net, we need to combine them with dot product to get scalar output values. However, in our modified architecture, we use a third network to combine the output from the branch net and the trunk net. So how do we do that? Is that, for example, for the first neuron of the last layer from the branch network, and we take the first neuron of the last layer from the trunk network, and we element-wise product them to so that the output becomes the input to the Z network, the third network of the first neuron. So first neuron product the first neuron becomes the input to the first neuron, and second neuron product the second neuron becomes the input to the second neuron. And so this is a modified architecture. I have questions.
So is this just a standard neural network, and you're trying to apply nonlinear activation function for the elements of the pointwise product, right?
Right. The third network is just MLP, fully connected network.
Right. So the difference, if there's no sigma there, then it would not make any difference. It's the same thing. If your activation function is one, is identity, then it's just the standard neural network.
Right.
So the only thing is the activation function here that you put on to make this a nonlinear pointwise product.
Right.
And which activation function you use for sigma? The same everywhere, the same that you use elsewhere?
The same, but it's not time-ish. I will explain it later. So
okay, that's fine. That's fine.
Yeah, we take a novel activation function. We find it is better than the time-ish. I will explain in the next slide. A few next slides. So so all the other things are the same, and we test our network compared with the vanilla deep nets. And we find in the training, our network can convert faster and get lower training loss compared to the vanilla deep net. And also interesting, if we look at the prediction, the solution of our PDs, we found that in our problem, the vanilla deep net cannot fit the sharp features in the spatial domain. What is shown in this blue and red arrows in the bottom panel. Or if we apply our architecture, we find the error becomes smaller and we can get a better fit. So, so here is a demo of how the machine learning tool work and how this can be useful. So this demo is, and the trainer network actually hosted on a website. You can scan the QR code on the top right to get access to this website on your phone. So on this website, the user can change the input parameters, and every time the let me play this. Every time the user changes the parameters, for example, I change the first parameter, and the network can predict the solutions in just 1 second. So all the things are run in real time in a website. This is very fast. You can imagine before this machine learning tool came out, astronomers need to run, for example, 1,000 or 2,000 CPU hours to get the solution for each pair of the parameters. But now with DeepNet, we can get it in just 1 second. And this can be very useful for astronomy studies. For example, here is an application to astronomy. Here, we want to study how the PD solution evolve with the changing of the parameter. For example, one of the parameter called the planning mass. And here is a movie to show you how the PD solutions are changing with different parameter values. And here I put 100 simulations. I put 100 PD solutions and get this movie. In traditional method, astronomers want to study the relation between the PD parameters and the solutions. They need to run 100 hydrodynamic simulation, and this is going to be very costly. It can take 100,000 CPU hours. But now this is too costly, and now with DeepNet, we just need to run it on GPU for 5 seconds to get this 100 solutions. And then the astronomer can start, okay, how the features in this solution changing with the increasing of the parameters. So with this deep net I discussed just now as a very fast machine learning tool that combine PD parameters to the solution, and we call it a fast forward problem solver. We can also use the same network to tackle to accelerate the inverse problem. So inverse problem, the goal is we want to infer the PD parameters from a given solution. We do not know the PD parameters. And the method we did about that is combine the PVD-ONet with the optimization algorithm called the CMAEX. So covariance matrix adaptation evolution strategy. So how do we do that? Is we use an iterative forward inverse approach. So here is the flow chart shows how one typical iteration goes. At the start of one iteration, we sample 100 set of parameters from a Gaussian distribution, and we feed this 100 set of parameters to our deep net. And this deep net will predict 100 solutions corresponding to these parameters, for example, in just 3 seconds. And once we get these solutions, we compare it with the solution we want to fit, and the difference are summarized into a bunch of scalar values. So we get 100 scalar scores. And with this pair of 100 set of parameters and 100 scores, we feed this into the optimization algorithm called CMAEX. And this optimization algorithm will give us suggestions on how to update the parameter sampling distribution for the next iteration. It will update the mean and the covariance matrix in the Gaussian distribution. And for the next iteration, hopefully the distribution will get closer to the ground truth value. And we run this iteration for many times until the PD parameter sampling distribution converge to the ground truth of the parameters.
Is the optimization loop gradient free, or use gradients? The CMAEX.
We do not need the gradients. So this is a gradient free.
Yeah. Thank you.
So here is one example to show you how the tool performs. So this is just one example, and in the top is the ground truth value of this example. But we have 4 images here. Is that we want to challenge our inverse problem solver. We not only want to give this solver perfect database, but we also want to input the noise image or image with missing pixels. So in the third image, we input we give the inverse problem solver, okay, we only have the inner part of this image. Or in the first, we only have half of the image. So we ask whether this inverse problem solver can still infer the PD parameters. And it turns out it was perfect. So you can see the top is the ground truth values, and in the middle is the inferred PD parameters, and it is very close to the ground truth. And once we get the inferred PD parameters, once again, we can use our PVD-ONet to reproduce or reconstruct the PD solutions. And you can see it is very similar to the data we have. And the error is very small. So here is just one example to show you how the inverse problem works, how the solver works. But here, actually, we have tested our inverse problem solver on 256 images with different parameters. And on the left is inferred PD parameters error distribution when there is only one single physical quantity but without noise. And on the right is we have 3 physical quantities. We use all the information to infer the PD parameters. But all these quantities are with noise. So these are 2 cases we show here. And you can see for both cases, the PD errors, the PD parameter inference errors are very small. And also I want to say, before this machine learning based inverse problem came out, how did the astronomer do is that they need to run many heterodynamic simulation with guess the PD parameter candidates, and then they compare it with real data. So you can imagine, because our computational resources are limited, we cannot run many heterodynamic simulation to infer the parameters from one image. For example, in typical literatures, astronomers run 50 to 100 heterodynamic simulation to infer one disk. So you can imagine the inferred parameters cannot be highly accurate. But with this tool, we can test the 10,000 parameters within just 30 minutes, and we can get a highly accurate inference of the parameters. So previously, I discussed two projects based on deep net and data-driven machine learning training method. So in the third project, we explored how to use physics-informed machine learning to solve equations. The motivation is that in the data-driven machine learning method, we always need to use labeled data to train a neural network. And in astronomy, because the Navier-Stokes equation is very expensive to solve, we cannot get a large amount of data from the heterodynamic simulations. And in this case, we need to find another way to train our neural network. We cannot get a large amount of data. We need another way. So that's why we explored the physics-informed machine learning. And the goal is that we know the physical laws clearly, and we want to use the physical laws in the mathematical format is the Navier-Stokes equation to train the neural network. And once trained, this network should give us an approximation to the PD solutions. So here is how the neural looks like. And this is a standard pin. You are very familiar with that. The input are the three coordinates, 2D coordinates and the time. And the output is surface density, radial velocity, and azimuthal velocity. And we tried this linear version of the pin, and what we found out is that in our problem, this pin cannot give us very good results, very good fit to the PD solutions. And we did some improvements to the vanilla pin, which is listed here from these 4 literatures. And we have some other improvements, but these are 4 major improvements we think makes results better. The first is a self-scalable time-each activation function. So this is also the activation we use in our deep net. And the second is a causality loss function. And the third is adaptive time marching strategy, so that we can have long-term prediction of the solution. And the fourth is the PD training point sampling method. Because we have sharp spatial features in the PD solution, we cannot use a uniform sampling. So we make denser sample on the sharp features. But today we do not have enough time to discuss the details, and just list the literature we get these methods. So here is one example of our preliminary results. So on the left is ground truth from hydrodynamic simulation, and on the middle is our neural network's prediction, and on the error is the red column is errors. And then we have 3 unknown physical variables. So let me launch this movie. You can see the neural network can predict some patterns, some features in the solution, but it cannot track the evolution of these sharp features for a very long time. And also I have radial velocity here, and also I have the azimuthal velocity. However, you can see that our prediction of the azimuthal velocity is significantly wrong, significantly off, and we are still working on to figure out why. But anyway, so in these projects, the major challenges we found is first, even though we only train the neural network to solve one PDE, so all the PDE parameters are fixed, only solve one PDE, we still found that the training of the neural network is much more computational expensive than running a numerical solver. So the efficiency cannot compete with the traditional method. And the second challenge is that we found the solution deviated from the ground truth as the time goes. So as the evolution time increase, we found the error compared with the ground truth increase, and we cannot suppress this. So the reason behind this is that we think because we cannot make the neural network obey the PDEs at every point and every time frame in the spatial time domain. So as a result, the PDE errors will accumulate as the time goes, and that's why we cannot track the ground truth for a very long time. So these are the three projects we have conducted or we are still working on. And so as I had discussed, the current pin only can solve one PDE at one time, and all the PDE parameters are fixed. And even though the efficiency cannot compete with the traditional method. So in our next step, so one method we are interested about is physics-informed deep operator network. It is a combination of the deep net and the pin. And the advantage is that it can solve parametric PDEs. So one train of this deep net, and once the train done, we can use this deep net to predict solutions for different PDE parameters value, as just what we did in the first project. So this will be one possible future project we want to do. But we haven't put our hand on it, and we would like to hear any suggestions or comments about this, and also about our pin project. And this is all I have today, so and I'm happy to take questions. Thank you very much.
Yeah, thank you, Shunyuan, for your presentation. We have plenty of time for questions. And is there any question from the audience or speaker? Sorry.
Yeah, there are many ways to do this actually, but I think the hybrid approach for the physics informed neural DeepNet is if you look at our paper where we did everything in variational form, that helps. But also we had like 10 or 11, I think, simulations, and then the rest was done using the physics informed laws, just like in the Sifan Wang's paper, but not just purely physics informed. I think that would be difficult. So you can only, instead of 450 simulations that you run, you can run 10 simulations plus the physics in the DeepNet laws. You would the physical laws. I think that will work. There's also last Friday we had a talk here by Shunyuan Mao from Xiamen Dashuan, where he showed how you can combine DeepNet and pins. So you can pre-train DeepNet in some conditions, and then pins you can run it for in fact for this type of problems with sharp gradients. So you may want to look at that paper. It's on the archive or the talk. If you go to Crunch YouTube, previous Friday, it's already the recording is there, so you can see the first talk is on this topic. But yeah, there are many variations of this, but it's an interesting problem that because you have interesting physics and very sharp features. Also, I was going to say also that maybe you can try training the DeepNet in 2 stages. There's another talk here at Crunchy YouTube. You can find that. That definitely will solve it.
Okay, great. Thank you. Thank you.
Yeah, Shunyuan just put the link in the chat for the video George just mentioned. GP Mao, he gave a talk about DeepNet last Friday. So you may want to check this link for the recording.
Thank you. Yeah, I will definitely want to check this video. Yeah.
I don't know if Ahmad is listening, but Shunyuan, the modification, you found that having this Z network, what you call after the Z network, where I asked you about this element-wise product, is gave you a very significant improvement, right? I can see here from the loss. So Ahmad, this is something that you can also try.
Sure.
You see what it is, Ahmad?
Yeah.
Okay. So at the output, a lot of people are playing with the output. They don't want the linear output like that. So they insert these non-linear elements. It's something that would work also for the tensor networks, the separable pins that people are doing. I think Chan should try that. I'm not sure if it worked for her, but it's it seems that here it worked very well for this case. It was a huge reduction error, factor 4 at least, 5, 4. Yeah. So anyway, thanks very much, Shunyuan. That was a good talk.
Thank you, George. Thank you, Joey.
Yeah, Shunyuan, I have a question about the details. So here in this slide, you're showing that this novel architecture about DeepNet, and previously we did this dot product linear elimination of the output of the trunk net and branch net. But here you add another nonlinear neural network after the branch and trunk, right?
Right.
Yeah. Okay. So what is the input of this Z network? So it's element-wise product of the outputs from the branch and trunk nets, or is like what is the input to the Z network?
So the first neuron input to the Z network is a product of the first neuron output from the branch net and the first neuron output from the trunk net. So
It's
for
a product.
example, yes. And you can also try other mathematical operations, but we use products. For example,
yeah. Oh, go ahead.
Yeah, for example, the output is the last layer have 50 neurons and the output is a 50 array, right? And the output from the trunk net also need to be a 50 array. And we product it to get another new 50 array and the input to the ZNet.
Yeah, got it. Is there any intuition behind the reason why you use product? So why just concate them, or why just add them together? So why do you do this product?
I cannot say it is intuition, but the motivation is that we first saw this panel. So we saw the vanilla DeepNet cannot fit the sharp features. And because in our solution, this sharp feature, the position of these sharp features depends on the input to the branch net. So it both depends on the input to the branch and the input to the trunk net, where is the sharp features. So we think, so this is a highly nonlinear relationship. We think maybe we cannot use dot product. So we want to learn this highly nonlinear relationship between the input of the branch and the input to the trunk. So we use another network. So this is the motivation, but I cannot give you more iteration about that.
No, it's fine. So I just want to ask why you use product instead of just add them, or like let's say in your example, like the output dimension of the trunk net and branch net are 50. So the simplest operation is just concave them into a
Right.
100 dimension vector and then put it into the Z network. So that's the simplest operation. So yeah, it's fine. It's fine as long as it works. The expressivity of the deep net is increased by a huge amount when
Yeah, what you
as
said just now,
yeah.
I think is can also I think probably can also work. But the important thing is that we need another nonlinear network.
Right. Okay. Thank you. Thank you.
Yeah. Thank you.
Is there any other question from the audience? We're waiting for our second speaker, so we have plenty of time. No? Okay, thank you, Shunyuan, for your presentation. You're welcome to stay here. I think we will start our second talk around 1 p.m. Eastern time, so it's about 15 to 20 minutes. So we'll have breaks and we'll continue shortly. Yeah. Thank you, Shunyuan.
Thank you, Dongren. Let me stop share and.
So are you stopping the recording?
All right. Our second speaker is Dr. Tengfei Luo from the University of Notre Dame. Dr. Luo is currently the Dorini Family Professor and the Associate Chair in the Department of Aerospace and Mechanical Engineering, with a concurrent appointment in the Department of Chemical and Biomolecular Engineering. Before joining the University of Notre Dame, he was a postdoctoral associate at MIT. After obtaining his PhD from Michigan State University, Dr. Luo focuses on nanoscale thermal transport, electronic thermal management, novel material design, and manufacturing and water treatment. Welcome, Dr. Luo. You may start your presentation.
Thank you. Thank you for the introduction. I think you're one of the best in pronouncing Notre Dame's university name, Notre Dame. I'm not sure if you did your study in France or not, but anyway, it's my great pleasure. This meeting is being recorded. I need to click OK. Thank you very much for the invitation and the opportunity to share our work in the physics-informed machine learning for solving a heat transfer problem. I know Professor Kenny Decke's group has always been on the top of the PIN community, and I did see one of your review papers on the PIN for heat transfer was one of the top viewed paper in journal Heat Transfer, where I'm a associate editor. That's for the heat transfer community. So here we're solving a equation that is a little bit different from traditional heat equation. It's a little bit more complicated, as I will allude to. But anyway, let me get started. So I'm presenting on behalf of a group of people who contributed to this work, and especially my collaborator, Professor Shunyuan Mao, who is, I think, is also very known to your community. So give you some background, since this is not a heat transfer community. Heat transfer is important, especially for thermal management, for the advancement of different technologies, ranging from, for example, space shuttles, turbines, as well as the microelectronics. Okay, so give you an example. If you are operating your iPhone and you are using the GPS for an hour duration, you will feel the iPhone become pretty hot, and that is the self-heating of electronics. How to manage the heat, how to properly make sure the heat transfer out of the active device region. It's one of the key problems that's limiting the further miniaturization of the electronic devices, for example, the transistors. One of the things is the heat is pretty localized inside the transistor. By the time you feel that your iPhone is pretty hot, the transistor temperature is much higher than what your hand would feel. Okay, so this is inherently a multi-scale problem, all the way from, for example, the warehouse for the data center to the circuit level, and then to the individual transistor level. Okay, so the size it's getting smaller and smaller. What it means for our heat transfer community is we have been trying to use different methods, different computational models and methodologies to tackle heat transfer at different scales. For example, the atomistic scale, nanoscale, mesoscale, and in the device, usually including the industry, people still use the Fourier's law. However, in the mesoscale, where the heat transfer is no longer fully diffusive, and the Fourier's law of heat conduction is no longer valid or can lead to significant errors. So in this case, Boltzmann transport equation is the state of the art. It sits in between the molecular level to the macro level as a bridge, and it happens to be an accurate tool that can model the heat transfer in these nanoelectronics or even microelectronics. So this page shows the heat transfer carrier in these microelectronics. It's mostly phonons. Okay, phonons are the quantum of the lattice vibration. So it's basically when you have the atom moving around, and that can be projected into the phonon space. You can think of phonons as particles, and they transfer from one location to the other. Okay, they can get scattered by other phonons or other defects. Okay, the time or the distance between the consecutive scattering events, it's the so-called mean free path. Of course, when we say mean free path, it's a statistical average. So this is a plot of the phonon's mean free path as a function of its frequency. Okay, phonons can have different frequency. You have extremely low frequency phonons. You can think of similar to acoustic waves, but you can have optical phonons that can interact with photons and interact with electrons. Okay, so there is a range of frequency. For this kind of phonons, their mean free path changes. For the low frequency phonon, they tend to have longer mean free path. For the higher frequency ones, they tend to have shorter mean free path. But anyway, there is a spectrum of different mean free paths. Okay, so if you think about the shrinking size of the microelectronics or nanoelectronics, when the size cut into the mean free path, okay, for example, the FinFET, the size is smaller than the mean free path of some phonons, they cannot get enough scattering. So in that case, those phonons would not transfer diffusively. Okay, that's why we need to consider the phonon-Boltzmann transport equation, because it can handle these non-diffusive effects. Okay, so this is just another plot for where the phonon BT is. All right, so from the diffusive Fourier's law to the purely ballistic phonon transport, in the middle, we have this region where we have semi-ballistic. So it's a mixture of diffusive transport and ballistic transport. And then again, that's where the phonon-Boltzmann transport equation can describe their transport behavior. So if you look at this phonon BTE equation, it doesn't look very difficult, right? So there is a time derivative, and there is a gradient, and there is a scattering term, but the details is it's difficult. Okay, so the difficulty is in the details. So usually if we, first, the scattering term is relatively difficult to evaluate. But in most of the cases, the so-called single mode relaxation time approximation, which convert this derivative to a simple difference, would work for almost all of the cases. But still, because we have these phonon particles with different mean field passes, and they can contribute differently to the heat transfer, we need to treat individual phonons differently. Okay, so that requires the so-called mode resolved phonon BTE to be solved. What it means is this distribution function F, now it's not only a function of like location, but also a function of, say, polarization, wave vector. This is solid angle. Okay, so it's in the reciprocal space, the phonons can have different directions. Okay, and then they have the solid angle, and you can have the wave vector. Okay, you can have polarization, and so if you are simulating the time dependent transient problem, then you would have time as well. And also, of course, the Cartesian coordinate, you can have XYZ for the 3D case, and the solid angle, you can have theta and phi. All right. So all of a sudden, similarly to a simple problem, simple equation become a very high dimensional problem. Okay. So this is just an illustration of what is the solid angle. For each phonon, you can have different angles in the reciprocal space. And for the wave vector and polarization, so this is the wave vector axis. There's different lines corresponding to a different polarization. So you can have all of these complicated relations or degrees of freedom that you need to consider. Okay, but anyway, so this high dimension making solving the phonon BTE very challenging using the numerical methods. Okay, so people have been looking at, actually quite recently, people look at using a deep neural network trying to solve the phonon BTE. I think Lulu from Yale, I think he graduated from your group. He presented some result when he was giving a seminar here using the neural network to say stimulate, learn from the data from phonon BTE. Okay, but the thing is, if you need those data, you would still need to use the Boltzmann transport equation to numerically solve the equation in order to obtain the data, right? So to give you some perspective, it can take hours to simulate the 2D cases, depending on how much you would like to discretize in the reciprocal space or solid angle space, and also the frequency space as well. So anyway, the bottom line is generating these data is not easy at all. So here comes right to your alley, where is the using a deep neural network to approximate the solution for PDEs in general. So phonon Boltzmann transport equation, it's just another type of PDE. Of course, because the nature of the deep neural network, supposedly it should be able to approximate the solution to this phonon Boltzmann transport equation without the need of numerically solving it using like numerical methods. Okay, so you know this better than me. If you basically train with respect to the residual of the PDE of the phonon BTE, you don't need any data. Okay, of course, as we'll show you later, sometimes data does help in terms of training. So we formulate the BTE residual into the loss function as well as the boundary conditions as well. That's what we had in this initial paper. And then we just train the neural network. You know this practice. But there are some special treatment needed in order to make the training better. For example, for the population, we have a subset of the network describing the equilibrium population and another subset describing the non-equilibrium component of the phonon population, and then assemble them together and then plug into the loss function for the training. And this turned out to be easier to train and give better accuracy. All right, of course, the students have tried different things and they come up with this kind of architecture. So needless to say, one benefit for the neural network is you can use additional parameters as like wildcards. And so when you train one,
Tengfei, can I ask you a question? Can I ask a
you
question?
want to? Sure. Yeah, please.
Hi, this is George Kariandakis. I want to ask you a question about the equilibrium. I thought you know the equilibrium state. So why you're predicting it? Or am I talking about something? F equilibrium, no, right? It's some sort of a Gibbs distribution or some known state that you, on the right-hand side is F equilibrium minus F. So F equilibrium we know, right?
Equilibrium, we do not. I think that is also part of the solution. So you give the equilibrium is related to the final temperature. The equilibrium is to.
Okay, but lattice Boltzmann F equilibrium is known.
Lattice, I don't think so. For a given problem, I don't think. For a temperature, at least no, but the temperature is evolving until you reach the final steady state, or the solution.
I see. Okay, maybe in isothermal flows, you know it, but not in, because it would be a function of that temperature, as you said.
It is a function of temperature. Yeah, I'm not sure if my student is here. He might be able to answer this better. I did ask my student to join.
In non-isothermal systems, F equilibrium is parameterized with the temperature and therefore depends on the asymptotic temperature, as you said, the steady state temperature.
Yeah, that's right. Exactly.
Okay.
Yeah.
That's why.
Yeah, that temperature it's being solved. Right. So it is the summation between the equilibrium part and the non-equilibrium part give you the total distribution, and that distribution corresponding to the temperature. And that's also it's something that we have to solve. Right. It's not directly known.
Okay, thank you.
Okay. Thank you for the question. So right. So if you train this neural network, if it is trained well, then of course it would satisfy the governing equation, and then it is the solution to that governing equation given a set of boundary conditions. Okay. And then, so this is another look at the residual and also the loss functions. And then, I was talking about the additional parameters. As you know, additional parameters can be valuable because with one set of training, we can use it to predict the different, for example, different conditions like the geometry of a transistor we want to simulate. So in that case, for a new situation, you don't have to retrain it, okay? So that is the benefit of the pin. Otherwise, if you take into account the training time, the actual time may or may not be similar to the numerical solver. Okay. So this is some of the result we obtained. we started simple using a 1D case where it's a simple slab where you have a high temperature side and a low temperature side, both the isothermal boundary conditions. And what we did is changing the distance between or changing the thickness of the slab, right? So as you shrink the thickness of the slab, you are approaching the mean free path of the phonons. Okay, so when the thickness is very large, you are in the diffusive limit, but when coming to like nanometer scale, you are in the ballistic limit. Okay, so this is what you are seeing. These lines have increasing thickness. As you can see, in the case of 100 micron, you would see just a linear temperature profile, which is the Fourier's law would predict, right? So if you solve the Fourier's law, it's just a linear temperature profile. However, if you go backward to the smaller length scale, you would have more like ballistic effects, and then there is a non-equilibrium effect. It's more important, and then you would get, say, the so-called temperature slip at the boundary, and then you have a non-linearity close to the heat sink and heat source regions. All right. So from this curve, usually we can get the so-called effective thermal conductivity. What we know is when your geometry size is smaller.
I have a question.
Yes.
On the.
Yes.
So you're talking about the thermal creep, I suppose, for the temperature slip boundary condition. But are you imposing any boundary conditions, or because in pins you don't necessarily have to impose boundary conditions? So I was wondering if you impose boundary conditions here.
We don't impose. If you say impose means a hard boundary condition, we did not. It's a soft boundary condition.
But it's still it's a boundary conditions on the, because you can
it's a boundary condition. Yes.
But not on T, right? You impose boundary conditions on the distribution. Because you're
Boundary
working
condition.
you are working with the phonon equation, the Boltzmann equation. So you can
Right.
apply like scattering types of boundary conditions on the distribution.
No,
Not on the temperature.
No. It's so actually in this equation we never have temperature. What we are operating is in the distribution space. Okay, our state variable is
Can you
is
go
the
back to that
distribution.
slide? You didn't explain that. So here the boundary conditions are. Let me see.
The boundary condition, we did not say this explicitly, but the boundary condition is like the integration of the population over all the solid angles would equal to would give a temperature that is the boundary temperature.
Right. So you don't impose anything on T. That's what I'm saying.
We don't impose that in T. Yes.
Right. So the thermal slip, the temperature slip or the temperature creep will be a result, not that you don't impose it through a coefficient.
No. Yes. We did not show the boundary point. Boundary point is always at the set boundary. So this is interior. This is the point. You can think of the point next to the boundary. So there is a very sharp gradient, or you can call it discontinuity between the boundary and the first point. So that is the temperature slip we usually see when there is ballistic effects.
Yeah, it's a jump. That's a slip is a jump.
It's essentially a jump. Yes.
Okay.
Right.
All right. Thank you.
Right. Yeah, no problem. Great question. And then from these temperature profiles, we can say predict the so-called effective thermal conductivity. And what we have known is for geometry that is smaller than the mean free path, you would have effectively lower thermal conductivity. Okay, so this was able to reproduce that curve pretty well. Okay, and the solid lines are the solid symbols are the points we have trained on using a parametric training, using L as additional parameter. And the open circles are the ones that are for prediction. So basically, it has some interpolation capability. The result looks very good. By the way, the black line is the analytical solution to this simple 1D problem. So the matches each other. So match the pin results very well. So we go to the 2D in plane. We have two adiabatic boundary conditions, and then we have a temperature gradient. So here, probably periodic, it's a little bit different from the conventional periodic. So we just make sure that the dt dx in this direction, it's a constant imposed by these periodic boundary conditions. Okay, and then we would have the heat flux as a function of this y coordinate. Okay, and we have these shapes, and then again the effective thermal conductivity also agree with the analytical solution. So when it comes to 2D, there's no longer analytical solution. At that time we were not aware of any open source effective phonon BTE solvers, but later in the past couple of years there are a couple of open source BTE solvers we can compare to, which we'll show later. But at that time they were not available. But anyway, for the 2D case, we did the simulation again using the L, which is the dimension, as the additional parameter. For the cases where we have ballistic effects, we could not compare to anything. But in the diffusive limit, we were able to compare just to the solution to the Fourier's law, and they match pretty well. Okay, and this is a 3D case. At least at that time, doing 3D numerical simulation for phonon BT, it's pretty challenging. We were not able to find code to do that, or there's only a couple of papers showing results for 3D simulations. But anyway, we just did the simulation at different length scales, okay, all the way from ballistic limit to the diffusive limit. And then the result looks reasonable. I think what we have learned from this study is pain would overcome of just circumvent the numerical challenges due to the high dimension, the curse of dimensionality. And for these simple geometries, no matter it's 1D or 3D, you can get pretty good results, okay? And additionally, we can use the parametric learning, and then we can say train one neural network and be applying it to say different geometries. Of course, if you look at the training war time, depending on the machine used, still can take hours, especially if you have 3D cases. But the inference time, it's pretty fast. And I think we can do much better than this now, okay, depending on how many points you want to sample in the inference.
Yeah, hello, Tengfei. This is me.
Hey, Lulu,
nice to meet
I
you
was
again.
just talking
Actually,
about you.
There's a question I should ask. So why for 3D your inference time is, let's say this is roughly 5-6 minutes. We are just one fold propagation. It should be really fast, right? Even if we have all the points.
No, we have more points. I think this is just proportional to the number of points.
But if you do the GPU, it could be parallel, right? And not necessarily really proportional. If we do 1 point by 1 point, it's proportional. Right?
You can, yeah, definitely. I wouldn't argue with that. At that time, we did not say we did use a GPU, but it's probably a 6-year-old, 7-year-old GPU.
Okay.
We did not intentionally so. For example, because we have more points, we try to parallelize the inference. we did not try to do that. Okay, we can't do that, of course.
Yeah.
But anyway, the point I want to make is the 3D case numerically, at least up to when we publish the paper, usually take many hours and many CPUs to achieve. Okay, this makes it possible. And thus let me see how about the time. Oh, okay, I'm growing much smaller than I wanted to be. So, okay, I think I can skip this part. This part is about creating a problem that has commonly seen in the phonon BT. Usually in the phonon BT, where we assume the temperature gradient is very small so that you can linearize the equation. But using some tricks in the pin, we can handle this problem easier. Okay. So, but anyway, I will skip this part.
You don't have to skip it because we're interested in the mathematics, not the results. I saw a mathematical trick. We are mathematics.
It's a mathematic trick. So, okay. So what I want to say is, let me try to go back then. Okay. Let me see how to do that. So if you think about the slab problem, okay, we apply a temperature, high temperature and low temperature. For example, the mean temperature is 300 K and the high temperature is 301, low temperature is 299. And then its population can be linearized. The local population can be linearized by the difference of the temperature from the mean temperature, because the temperature gradient is not very large. But when you have very large temperature gradients, so I gave some examples. For example, laser processing, or you can have a very high temperature hotspot, you will end up having a very steep temperature gradient. And this treatment, the linearization, it's no longer valid or no longer accurate. So what we try to handle is represent, add additional pre-trained shallow neural network to consider this nonlinear population with the temperature, and then we can still keep the main part of the neural network similar to the previous one, so as to solve this specific problem. Okay, so this is the
what?
Yes.
Oh, I see. I see. Yeah, I see.
Yeah,
I see.
We're going there. Yeah. We're going there. Yeah. So usually, if the temperature difference is relatively small, this the beta is a constant, so you can expand the equilibrium population around this reference temperature. But when this temperature difference is large, this is no longer constant. So what we have learned is this beta as a function of temperature, so that we can easily express, even if this temperature deviates a lot from the reference temperature, for example, the 300 K I was saying, you would still be able to, say, map the local temperature to the equilibrium population. Okay, so there are some mathematical manipulation. So this is the how to say, the energy conservation equation. Okay, so if we plug in this expansion into this energy conservation equation and do some manipulation, we can have a T star, and by setting a T star to be T to be 0, which can be imposed in the loss function, we are forcing this energy conservation. Okay, so instead of having a direct energy conservation equation in the loss function, we just replace that into a t star minus t to be 0 in the loss function. Okay, so in that case, we can properly train this neural network, and then we have, say, apply this method into the silicon cases where we have a large temperature difference. Okay, we're talking about tens of degrees or hundreds of degrees. So in that case, for example, if we have a very small, very thin slab, temperature, the thickness of 10 nanometer, I set one side to 50K, the other side to 40K. That's like 20% temperature difference with respect to the high temperature side. So in this case, you have the ballistic effect. So basically, the phonon in this case does not get scattered. Okay, does not get scattered at all. In that case, you would approach like a phonon radiation limit. It's almost a linear, it's almost a flat temperature profile. Okay, so in that case, you only have the thermalization at the boundaries, but not inside the material. Okay, and we also look at the diffusive limit where we have larger size of the slab, but large temperature differences. And again, this new model was able to track the Fourier solution pretty well. Again, this is 100 micrometer, which is in the diffusive limit. And we have 2D cases, and we have 3D cases. Again, no BT solution. I don't think currently there is a numerical BT solution that can explicitly handle large temperature differences. They still use the linearization approximation. But anyway, so this model was able to, say, capture that. And if we compare to the Fourier solution in the diffusive limit, they compare very well. Okay. Of course, these are steady state solutions. We have also looked into solving the transient phonon-Boltzmann transport equation as well. And I would just, it's nothing fancy, which just add another, just add the temperature as another parameters to this neural network. And we were able to train the neural network, and we were able to, say, predict the transient temperature decay of a sinusoidal wave pretty well. Okay, as you can see from these from these panels. Okay. So we have 1D cases, we have 2D cases, and then, yeah, so they look reasonable. Again, there's no numerical solution we're able to find that can compare to our results. Okay. So that's the phonon-Boltzmann transport equation. Actually, many of the physical processes I described, there are multiple carriers besides phonons. Okay, for example, if you use a laser to process a metal surface, there is electron absorbing the laser energy, and the electron dump the energy into the lattice, and then the lattice would transfer the heat away. Okay, so multiple carrier thermal transport, it's something people know, but they always have to use significantly simplify the equation to solve these problems. Okay, for example, the 2 temperature model and so on and so forth. So this kind of multi-carrier transport phenomena is relevant to like energy materials like thermoelectrics and electronics, because in the electronics where the heat is from, it's basically from the electron phonon interaction. So electron would transfer from the source to the drain, and they would collide with phonons, and then its energy get dumped into the phonon degree of freedom. So in this case, what we need to consider is the coupled transport between the electron and phonons. Okay, so fortunately, electron transport can also be described by the Boltzmann transport equation. Okay, so you would have the coupled Boltzmann transport equation, one for electron degree of freedom, the other for the phonon degree of freedom. And how they interact with each other is through this scattering term. And that scattering term can be either derived from experiment or calculated from first principle calculations. So to solve this coupled equation properly, my student actually constructed the new architecture where we have a subnetwork for the phonon degrees of freedom and subnetwork for the electron degree of freedom. And then they assemble these together, and then apply the boundary conditions as well as the initial conditions, and then train it. And so the solution, the neural network, would satisfy these governing equations. Okay. So in that case, we were surprised it trained pretty well, and then it was able to say, well, I don't think I should say it's surprised. There were some struggles, but eventually we got it to work. So we're able to simultaneously solve the coupled electron and phonon BT solution. And I believe that is the first time it was actually solved. So some test cases where we dropped the drift term for our first. We dropped the drift term. That means it's just how to say, just isothermal conditions. I wouldn't say it's not isothermal. It's just a uniform temperature for the electron degree of freedom and the phonon degree of freedom without spatial variance. That's just the first simple test case. And in this case, there are like analytical numerical solutions. And we were able to simulate that situation pretty well. What it does is we apply the electron temperature to be a high temperature and the lattice temperature to be much lower. And over time, because of the energy communication between the two degrees of freedom through the scattering terms, the temperature would eventually converge. Okay, so this is what's happening in the laser processing, what's happening in the hot electrons in the electronics. And also we did add the drift term later, and we simulate a 1D case, and there is some numerical solution as well. But anyway, what I want to say is they were able to reproduce the results pretty well. Okay, and 2D cases, and this is 2D case. So this 2D case, let me see. So we changed the length scale of the sample, and then as the length scale changes, as the length scale become larger, it would allow more space for the electron phonon to interact before each them reach another boundary. So that's why when you have larger samples, you turn to eventually reach equilibrium between the electron degrees of freedom and phonon degrees of freedom. But in the case where you have small samples where the scattering is not sufficient, your temperature would never converge, okay, before the carriers reach the other side of the sample, which is physical. But again, there's no way we can verify it from a numerical solver up to date. Okay. So we have, we did, because there are more degrees of freedom in terms of the solution input, but we still try to, say, add additional parameters inputs as a wildcard. So here we use the aspect ratio as the additional parameter. Okay, as you can see, this is the aspect ratio. And then we trained against the aspect ratio as additional parameter. And when we do inference, the result again come out to be physically reasonable. Okay, but numerically, quantitatively, we were not able to find the benchmark to compare to. All right, so this is 2D transient heat transfer involving both phonon and the electrons. You can think of a material, you have laser pulse to heat up the electron degree of freedom at the surface and see how electron transfer heat. Okay, so this is how electron transfer heat and how it dumps the energy into the phonon degree of freedom. And then phonon will transfer heat away on top of the electron degree of freedom. So, which is quite interesting to see from the result point of view. So we have been like developing the pin for these different kinds of equations, different situations. Recently, we are studying an effort to actually apply the pin to realistic geometries. Okay, previously it's all rather rectangle or 3D cuboid, but now we want to simulate like a transistor, FinFET transistor. In the FinFET transistor, you have a silicon base, and then you have these fins. These fins are the actual transistor region. So you would have a source region, you have a drain region, and you would have a gate. So this is where you do the computing, okay? So voltage is applied between the source and drain, and the gate would change the gate voltage would allow you to have on and off. So heat transfer from the source, the electron transfer from the source to the drain, and then because the electron phonon interaction, you would have some heat generation in the gate, underneath the gate region, but it's still in the silicon. By the way, everything is silicon. So we started by simulating a single transistor and taking into consideration the symmetry. We just kept half of it just to test whether the pin actually works. We went off simulating this geometry. And again, recently we were able to find a numerical solver, and this numerical solver, I have to say, is quite powerful. It was able to simulate a FinFET transistor numerically, the phonon-Boltzmann transport equation in like tens of minutes, okay, no longer hours. And then what we have seen is if using this BT numerical solver, the hotspot temperature, which within the fin, the temperature would increase by almost 200 Kelvin. And this 200 Kelvin increase is about 170 Kelvin higher if you use a Fourier's law to solve this problem. Okay, so that means the phonon Boltzmann transport is really needed if you want to predict the hotspot temperature in this FinFET nanotransistors. Okay, but anyways, so coming back to the pin. So for the new geometry, we call it irregular. It's not that irregular. It's just one rectangle with another rectangle on top of it. And we start with the 2D problem. And in this case, even if we make the transistor not nano, okay, in the macro scale, we just blow up every dimension by 100 times to ensure every point would be like diffusive heat transfer, so that we can compare to like a Fourier's law solution. Just by adding this small fin to this rectangle, training becomes exponentially more difficult. We were not able to train it well. So if you look at the pin solution to the COMSOL solution in this case, they don't match well. Okay, so we were looking at different solutions, and then what we did is we tried to add 10 points, data points from the COMSOL solution to our phonon BTE pin. And by adding some points, it was able to train it much better. So in this case, we believe the points helped the training to find global minima. However, still, this is in the diffusive limit. Okay, next step, we shrink everything back into the realistic geometry to like the nanometer transistor. And in this time, whether we add data point or not, we're not able to train it well. Okay, so this is the numerical solution from this GIF-BTE, which is the open source numerical solver. And in our case, we're not able to train it to this. This is the result we have trained. We have tried a lot of different things trying to improve. But until recently, we were able to make some progress to train it. We find actually it's the number of points we sampled. We always thought because the fin has a more ballistic effect and the temperature gradient is much larger than the base, we need to sample more points here. It turns out that's not true. So but if we sample more point in the base, okay, we actually get a much better solution. Okay, that's what we have learned by try and error. And then actually, I wanted to present this result. Hopefully, I can get some advices from this audience in terms of how to handle, I wouldn't say complex geometry, I would say a little bit irregular geometry, how to train the pin better, whether there is a way to train the pin better. Okay, so this is, we also tried other like a training point distributions. We're not able to, still, we cannot get better result, actually. So I can stop here. I think the purpose of this presentation is to introduce what we did, how we brought a brilliant idea of pin from your community to the heat transfer community, but how we are now seeing problems when applying these techniques to realistic cases. Thank you very much.
Thank you, Dr. Luo.
Yeah, thanks, Tengfei. This is a very good application of pin, especially in high dimensions. So that's, yeah. To answer your question, it's actually a very trivial fix. And that is using a C-pin. A C-pin is a domain. You basically use the domain decomposition. So in the big domain, you will have one pin. In the small domain, you have another pin. Okay, and then
we tried that. We did try that.
No, see, pin or X pin would work because you can then tune each network with different activation functions. If you try, for example, I would use in the small domain, I would use adaptive activation function, and then Ameya, who is the author, just put on the chat the paper. But maybe Ameya, you can work with them to help them to use synergistically both the adaptive activation functions and conservative pins.
Sure. Okay. That would be great. Actually, we were having a meeting on this topic this morning, and Jianxun raised this C pin or interface pin using different using different activation functions. I'm glad I present our failed cases that you can give advices.
Yeah, I'm sure it will work if it is done properly. The interface conditions you have to be very careful for the case that you had only one equation, not the electron phonon.
Right.
I think that's the straightforward application. When you have the electron phonon system, you have to be careful to have the right fluxes at the boundaries. But I think the boundary conditions that you have, I mean, you can formulate that actually by just taking the variational form of these equations. You can see which fluxes, just like we would use in discontinuous Galerkin methods. Same type of fluxes.
We never explicitly calculate the flux. The flux is determined by the phonon energy's solid angle dependency. So if you, for example, the phonon can propagate in all the directions with the same amplitude, you have zero flux. But if this sphere is skewed to one side, then you would have flux in the other direction. But we never needed to explicitly calculate the flux in solving this equation.
No, not the flux in the temperature, but the flux, I should say the Neumann, the gradient. The gradient, for example, what you will match at the boundary will be the state, for example, f, the distribution function, as well as its gradients. Let's say that.
Yeah.
The gradients.
That's also direction. Yeah. That's also what I'm trying to say. Maybe that's something additional we have to impose. But flux, I see. We've never applied flux.
Ameya can help you to get the. I think X pin may be more appropriate here because you're dealing with a f, the distribution, not with a conservative quantity, right, which is the conservation law. So maybe there's another version called X pin. So X pin imposes continuity of the residual, continuity of the states, and or continuity of the normal gradients. But you can also try normal tangential gradients.
Okay. Yeah, definitely try those. So
then also in terms of the sampling, you can use different sampling techniques in the big domain, the small domain. There's several papers now on sampling, including one from Lulu's group and many others. One just came out in CISC, I think, Science Journal of Scientific Computing. But there's several papers on sampling that improve because you show some sensitivity to it. So
yeah, there's definitely a lot of sensitivity to how we sample the point. Yeah, we're trying to sample from a physical point of view,
and since this is a first order system, you could also apply G-pin, where you also take the gradient of the residual. G-pin also is a student with Lulu produced a paper, G-pin. So that definitely works better. So it's more expensive, but your system is first order, so you just have to do second order derivative, so it's not that expensive. Because you have to take the gradient of the residual, so the residual has first order derivatives, you have only second order derivatives, which certainly JAX is not expensive.
Okay. Okay. Yeah, we'll definitely try these. One question I have is if we decompose, like for example, the small rectangle from the large rectangle, each using a pin, how would the number of pin would scale? In a realistic transistor, I would end up with a huge number of these small rectangles, right? Because we
Yeah,
have
so
different materials, different
Right.
like
yeah.
those
I
shapes.
mean, when you scale up, you have to use more GPU. So typically, what we do, we put one of the subdomains into a GPU, separate GPUs. So how many fins would you have? Hundreds?
We can go to hundreds. This project asks us to do 300,000. I'm not sure we'll ever use a pin to solve the whole problem. But even for one pin, you think about this. So these like white stuff, it's not actually voids. So they have other materials we're not simulating yet. We have other materials, for example, there's another layer of material here, and then that probably means this part would have one pin and this part another pin, and then I have another material on top of it. So even if it's a one transistor, it's going to have a lot of small domains. I inference is one thing, but I think training is going to be quite troublesome.
Yeah, but I mean, if it's a small domain like that, it's a multi-scaling space. So you really have to decompose the domain. No matter how you do it with finite elements or whatever you do, you have to decompose it properly.
Okay. Yeah, that's something definitely we need to look into. Thanks for the suggestions.
Yeah. I was interested if your student is there. I want to ask him a question about the. I saw that he's scaling with a pre-trained network. That's a neat trick.
Yeah.
Is he there? We can ask him the details.
He graduated. I do have
Okay.
other student here. I'm not sure if my other student can answer this question. Jiahang, are you here?
Yeah, I'm here.
Okay, I do have another student who did not work do this, but he's familiar with the details.
There is another slide. There's another slide that you have the that scaling with a pre-train. No, if you go even further back, earlier he had so scales with a pre-train pre-train shallow network or something like that.
Like here?
No, it's a sketch of a neural network, and then it's a sketch of the neural network, not the results. Yeah. Well, yes, this one here on the top, pre-trained shallow neural networks, but he used it for scaling. Somewhere else, they had the word scaling, scaled with a pre-trained. Maybe the student knows what I'm talking about.
Yeah, like here. There is a word on scaling.
Yes, in one of your slides it says like that. It looks like that says pre-trained for scaling. Yes.
Oh, maybe the electron phonon coupling case.
Oh, really?
Yes, you're right.
Right here? Oh, here. Yeah.
Oh, yes, this one. Yes, this one exactly.
Yes.
Yeah.
Mm-hmm.
Can you explain what you mean by that? Because scaling is very important actually for stiff problems, and so can you explain what you did, the student?
I didn't do this, David, but I can kind of explain this. I know he was actually trying to find the relation between the TE and the T phonon, the relation between the temperature to the equilibrium and non-equilibrium distribution. When we have when there's I remember this is for if for example, if that is a small temperature and we only consider phonon, it is linear. The relation between T and F is linear. But when we consider both phonon and electron, this relation can be complicated. So that's why he used a pre-trained neural network to scale, say, to construct the relation between temperature and distribution.
Okay, I think what George is thinking, the scaling is to scale the order magnitude, so they are around the same order magnitude.
Yes.
I don't think this is scaling here means that. It's similar to the page I showed previously. It's a pre-trained neural network trying to say map the temperature to the distribution, even though they have a nonlinear relation.
I see. Yeah. Mm-hmm. So instead of the linear, because you are doing like superposition, now you're doing something else.
Yeah. So actually, we did have a lot of different amplitude in the different terms. There were a lot of some manipulation of the original equation, so the loss function more or less are on the same order magnitude. At some point, we were also trying to scale different terms as well. That might have helped, but a lot of details the student figured out.
Yeah, that's why we should never let the students graduate.
If I have the option to do that.
We lose the details, yeah.
Yeah. The worst case is the student does not stay in this community after they graduate.
Yeah.
They do something else. Okay, any other questions? Well, if you don't mind, I will get in touch with your student who does the C-pin or X-pin.
He's actually he's assistant professor in research here, so
okay.
You get more than the student's opinion.
Okay, all right, sure. Your group member.
I already sent you an email, so we can chat later.
Perfect. Thank you so much. Yeah. Right. This is a very valuable opportunity for me because I was able to ask questions.
Also made the activation, adaptive activation functions may also help them for that. May help.
Right.
Yes.
For the two, when the composition, because it's that's the geometry brings multi-scale.
Okay. All right. Stop
Thank you very much.
Yeah. Thank you for the opportunity.
Yeah.
See you later.
Bye.
Bye.
All right, so this comes to an end to this week's seminar. Everyone has a good weekend. See you next week. Thank you, Dr. Luo. Bye.
Thank you. Bye.